So, now we look at the fifth problem of the tutorial 5. So, here we are given few channels of the EEG signal and we have to use the Welch procedure, that is how to compute the average PSD. Okay. So, we have to study the change in the PSD with respect to that when we change that window width, number of segments averaged and the type of window used. Okay. These three variables, and we have to compare the PSDs computed with respect to the PSD computed with the entire signal. That means, without averaging, if we take the entire signal and compute the PSD, what are the changes we get with different window width, different number of segments and type of window. Okay. And we have to discuss about the result at the end. So, that is the task given to ask. So, to start that, first we have to download the signals, that 4 EEG signals are given, EEG 1, C3, C4, F3 and F4. Okay. 4 EEG channels are given and they are given here in this location, and the corresponding MATLAB file to read and plot them is given here. So, we need to keep them in the same directory, that is the working directory of the MATLAB. So, now first we read those 4 signals. So, what we do, that we load first that F3 signal, name it as EEG F3, and sampling frequency is 100 hertz. So, we first look at that what is the length and we set the time axis, we plot that. So, to plot all the signals, we divide that plot area into 4 parts with the subplot command. Okay. So, first we plot that F3, then we read F4 and we plot F4 in the second location or second row we can say. Then in the third row we are plotting the signal C3. Okay. Here we are plotting that, and in the fourth row we are plotting that signal C4. Okay. Here we have done that. So, let us see that how these 4 EEG signals they look like. Here are the signals given, one below the other, starting with F3, then F4, then C3 and C4. All the signals they seems to be bit correlated, they have similarity with each other. So, now we have to go for that computation of the PSD. So, we compute the PSD of each one of them at a time first for the whole signal, and we display them, and then we go for actually the step of the averaged periodogram. So, for that we have to calculate the PSD first of that complete signal. Okay. For the complete signal we calculate the PSD of a channel, and we do it for all the channel. Then we calculate the average PSD by dividing the signal into finite segments and compute the average of PSD of the individual segments. Okay. And here we have taken these segments, they are non overlapping. Okay. And for that for the average PhD, we use the rectangular window and study the effect of varying the duration of the window, which will automatically come that if we change the number of actually segments, okay, because total signal length is fixed. If we reduce the window size, we have more segments, okay, and we repeat the same thing with Hamming window. Okay. And in that case also, by varying the window duration, what is the impact we would note. So, let us proceed. First, we are showing the PSD of the EEG channel, that EEG signal of channel F3. Okay. We get that DC has the peak, then there is some peak near, I think around 9 or 10, around 10 actually there is another peak. Go for the second signal F4, again the same nature is there, the maximum energy is there at the DC and there are peak around 10. Then go for the channel C3, that we get that around 10 the peaks are even more pronounced, and now go for that C3 and then C4, we get same nature, that C4 has that spectrum, though signals strength is there around 10, that it is less than that C3. Here was the C3 and here is the C4. Okay. Now, all the spectrum they are for the entire signal, and we get each of these case that there is high variation in the PSD or PSD, we can say they are having a lot of fluctuations. So, now we go for different segments. So, starting with 3 segments. So, how do we do that? We divide the signal by 3 parts. We are taking length of 750, total is 750 is the length. So, length of each of the 3 segment would be 250 each. Okay. So, we calculate the FFT and take the average. Okay. So, with that we can get the output. Let us see that what we get. Okay. Now, for the Hamming window it would be almost same, the only difference would be that previous case we are taking the that part of the signal directly. Okay. Here is the difference, that for the rectangular window we are showing that directly we are taking the part of the signal and we are computing the PSD. Compared to that, when we are going for Hamming window, we are computing the Hamming window and multiplying the signal with the Hamming window, okay, for that many samples, and then rest of the thing would be same. Okay. Now, here is the output we get for the 3 segment. We get the variation has been bit reduced compared to the entire signal with 3 segments, and here we are taking the rectangular window. Next, we go for that Hamming window. Okay. In case of Hamming window, we see it is little more smooth, but then again that the peaks are becoming little more wide. Next we go for 5 segment for the rectangular window. We see it is smoother than the 3 segment one. Okay. And now go for the Hamming window with 5 segments. Okay. So, here we get that the side peaks, they are getting merged in the Hamming window. If we have gone for the previous one, you see that compared to that rectangular window, the Hamming window is giving actually smoother one, but again at the cost of that frequency resolution. Next we go for that rectangular window with 10 segments. We see that the side lobes, what we are showing here, they are getting merged, okay, and we get the same nature for the Hamming window also, but the signal PSD looks much more smooth. So, this is all these things we see for the F3. Now, we go for the other channels. We go for that the signal F4. Okay. Before that, we would like to see them side by side. Before changing the another channel, we would like to see them side by side, and in the left hand side we are getting that the results for rectangular window, right hand side we get that for the Hamming window. So, if we look at the compare that left and right, we get Hamming window always is giving smoother PSD, and at the same time we can say that rectangular window is giving more sharp peaks. And if we now go from top to bottom in any of them, that for the rectangular window or Hamming window, we see as we increase the number of segments from 3 to 5, 5 to 10, we get more and more smooth PSD. But along with that, what we see that smaller peaks, they are getting merged. So, that is that downside of it. So, that is we can say the overall assessment we get for that F3 channel. Next we go for F4, start with the signal of the 3 segments with rectangular window, and then we look for that average of the 3 segments, that of the first the rectangular window, then Hamming window, then look at the average of that 5 segments of the rectangular window. We see it has become more smooth than the 3 segment version, and when you go for rectangular window to our Hamming window, then we get it becomes even more smooth. When you go for 10 segment, we get the rectangular window, it is more smooth compared to the 3 and the 5 segment cases. When we change from rectangular window with 10 segments to Hamming window with 10 segments, we get even more smooth PSD. So, now we put them together to compare, and like the channel F3, we see the F4 also gives us the same kind of conclusion, that Hamming window gives smoother PSD, and irrespective of the window, if we increase the number of segments, we get more and more smooth PSD, but we may lose actually peaks in that way, because they are getting merged as the frequency resolution is becoming more and more poor as we are taking more segments to average. Now, we go for channel 3. First, we look at the result of 3 segments, then we get the result of Hamming window 3 segments, then for 5 segments for rectangular window and 5 segments for the Hamming window. Then we go for 10 segments of the rectangular window followed by 10 segments of the Hamming window. Now, we put all of them together and we see in the left hand side the rectangular window is used, right hand side the Hamming window. Using Hamming window we get more smooth PSD, and for that that Hamming window not only we get it smooth, the smoothness also increases with number of segments, but at the cost of that frequency resolution, or in other word what we can say, the smaller peaks they are getting merged to give a bigger peak as we increase the number of segments or reducing the dimension of the or the duration of the window. Now, we go for the channel 4. We start with first the 3 segments with rectangular window. We get lots of undulations, but it is undulations are less compared to that the PSD when we take the entire signal. Now, we change the window from rectangular to that Hamming window and we see that we get a little more smooth that PSD. Next, we increase the number of segments. For the rectangular window we get it is more smooth. For the Hamming window it is even more smooth. For 10 segments for the rectangular window we get the best or smooth actually the PSD compared to the 3 segment and 5 segment cases, and for the Hamming window with 10 segments we get it is even more smooth. So, we put all of them together to get a perspective that how they are changing. We get the sharpest peak we are getting or sharper peaks we are getting for the rectangular window, and among these examples for the 3 segment average for the rectangular window is giving the sharpest peak and more undulations. As we change from the Hamming window in each of these case we get less actually undulation or smoother spectra, and if we go for more number of segments, that is smaller duration of the signal and more averaging, then we have that decrease in the frequency resolution, at the same time we have smoother PSD. So, these are the results we get. Now, we summarize the results. First, we look at the PSD obtained from the single channel of EG. It has very high variance or the undulations are very high, we can say. Next, what we get that if we use that average PSD, it helps to actually smooth out the PSD compared to the PSD of the complete signal. Okay. And next observation what we get, as we increase the number of segments, that is number of segment used for averaging, we get more smooth actually PSD, but this smoothness comes at the cost. As the number of segments are increasing and thereby the size of the window is decreasing, the frequency resolution is decreased, and what we get? We get the spectrum which is more smeared. That means that if we have two frequencies, they are very close to each other. If we are having more and more segments and thereby the window size is keeps on decreasing, these two peaks can get merged. Now, we have, let us look at few more observations, that when we look at the PSD in each of these cases, we see that apart from the peak at the DC, we have peaks in between that 9 to 10 hertz. That clearly indicates that the presence of alpha rhythm. Okay. So, each of these case alpha rhythm is the prominent, actually the signal that what we get. Now, we look at that what is the window use and what is the impact on that. For the rectangular window, we have smaller main lobe, and because of that we are getting sharper peaks, and compared to that the Hamming window, which has lower side lobes compared to the rectangular window, it is giving more smoothing. So, with this we conclude the fifth experiment of the tutorial 5. Thank you.